We conjectured that string theory in a 10-dimensional curved spacetime, which is AdS5 times S5, is equal, it's dual, it's an absolutely equivalent description, to a much simpler theory, which is just a quantum field theory called n equals 4 super Young-Mills in 4 dimensions. So we take just a simple vanilla conformal field theory, and apparently the claim is that it describes full quantum gravity in some higher dimensional spacetime. We did not derive this statement, but as I said, we provided several lines of thought, several different hand-waving arguments. Each of them you can say it's a 6 out of 10 or something like this, but you have many. Okay. So I think this is reasonable. So we had the idea that there should be some kind of map between volumes and areas in quantum gravity, because all these considerations of black hole physics was hinting at that. We had some intuition from considering some kind of brane construction that there should be some decoupling argument and some low energy Gedanken experiment that should lead to such construction. We knew that there should be some kind of string theory because we had this large N expansion where we understood that gauge theories look like string theories. And then we said that if we were to ask in which spacetime the strings live, because we knew by this theorem of Witten and Weinberg that they could not live in flat space, so we had to guess what spacetime it is, that in fact, if you want to guess a spacetime which has the isometries, which has as isometries the symmetries of n equals 4, you land very naturally on AdS5 times S5, the AdS being because the theory is conformal, and the sphere because we have this symmetry with which rotations of the scalars. We also said that these kind of dualities are natural if we think from the point of view of thinking of the holographic direction as some RG scale. Then we went and found some concrete evidence for this duality in the form of seeing that both theories not only have the simple symmetries, not only share the simple symmetries, that is rotation symmetry, the isometries, very global symmetries, but they also share these more mysterious and more powerful integrability symmetries. So we saw that if we consider some excitations, and let's see what this picture means, and if we scatter these excitations, we saw that they scatter in a factorized way. And what do these excitations mean? If the coupling is very big, this just means that we have some string and some classical ripples of my string. This is my string. And these are string ripples, string excitations. And we showed, indirectly, but we did, we showed that this scattering is factorized. We did not show this directly, but we know this is an implication of the fact that there exist many charges, and this in turn follows from the existence of a flat connection which depends on an arbitrary spectral parameter u. This is what you saw in the exercise. You constructed explicitly this flat connection, therefore you know that there are all these charges there, therefore you know that we have these bumps factorizing. What is the picture if the coupling, if the 't Hooft coupling is very small? If the 't Hooft coupling are very small, these excitations, I can think, are just Magnan's excitations in my vacuum, which is just spins up, moving in my spin chain. Okay? And these are Magnan's or spin chain excitations. And these spin chain excitations, if we scatter them, we saw they scatter in a factorized way. And then the way we were interpreting the fact that we observe integrability at strong coupling and we observe integrability at weak coupling. And then we can say the following. We can say we have a string theory. When the string theory is classical, we have integrability. And this is probably not broken at the quantum level, because we know that if we quantize, 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 and get to super quantum vibrating strings, which will be the picture on the left, we still have integrability. So then, it leads you to believe that when lambda is finite, which is the regime where Yang-Mills is hard, but string theory is also hard, whereas here, string theory is easy, and Yang-Mills is hard. And here, of course, string theory is hard, and Yang-Mills is easy. And in the middle, this is really the hard part, is when we are at so-called finite coupling. Yang-Mills is very tough. We don't know how to describe quantum field theory at finite coupling. String theory is very tough. We don't know how to describe strings when the string tension is finite. But we believe that it would be such a huge coincidence that you start with these charges, and then they would stop being conserved at the quantum level, and then be conserved again at the very quantum level. This is a bit unreasonable. Said differently, if we start from the field theory, we say we have some magnons, they start interacting with each other in a factorized way. We start including longer and longer range interactions. Perhaps they will no longer factorize. But then, as we include many, many, many and go here, they factorize. Okay, it's reasonable to assume that in the middle they also factorize. So this, if you want, is a conjecture that the theory is integrable. But then this conjecture motivates several computation. It tells us we should go and compute at weak coupling and see if it is true. We should go and compute at strong coupling and see if it is true. And if it is true, then we know what the fundamental object is. And the fundamental object, if we want to completely study the theory, is the 2x2 S matrix. And it is the dispersion relation of each excitation. If we know these two objects, the S matrix, which is a function of momenta P and K, and the dispersion relation, which tells you what's the energy of a particle, then we can solve the theory. Okay? So if you want, the goal, if we want to solve this theory, either string theory or gauge theory, or you can call it whatever you want in the middle. You can call it the ADS-CFT model. If you want to solve it, those are the two quantities you should aim at. Okay. Any question? So this kind of observation, the fact that we make a guess and then we find integrability in both sides, I would add this, if you want, I would add it as an extra arrow to our box. But it's an arrow in both directions, of course. You can put them as you want. If you trust ADS-CFT, you see that it's nice that indeed it's integrable. If you don't, you would say that this supports ADS-CFT. Yes?
So we saw that we have some conserved charges because of our flat connection, but how do we know that those charges correspond to factorizability?
What you would have to show is that you construct your holonomy, you integrate your flat connection around it, and this is conserved. So that means that you can expand it, for example, around spectral parameter equal pi over 3, and all terms in the Taylor expansion are conserved charges. Now, if you expand around some random value like pi over 3, however, these charges, if you try to compute them explicitly, are very non-local and crappy stuff. So what you have to show furthermore is not only that you have infinitely many charges, but there is one point in spectral parameter around which, if you expand, you get nice local charges. By a local charge, it means that it's an integral around sigma of something with 2 derivatives, then 3 derivatives, then 4 derivatives, and so on. Like we had for the spin chain. If we took log of the transfer matrix, it was first nearest neighbor, then next to nearest neighbors, then next to nearest neighbor, and so on. And it was because there was this notion of locality, which in field theory would mean 1 derivative, 2 derivatives, 3 derivatives, that you could argue that will be factorizability. So one more step here is the existence of a point around which the expansion is local. Like when we had spin chain construction of our matrix, remember, what was the key ingredients? It was that R obeys Yang-Baxter, but one more was that at a particular point, R was just a permutation operator, because this was guaranteeing that the resulting Hamiltonians were nice local objects. Okay? So here in this arrow, there is one point hidden, which is that we must find that indeed the charges are not just infinite, but they are local. Now let me just recap a couple of things that we have seen in the exercise in the homework. Because we want to know a little bit more, I want to tell you a little bit some geometrical things about ADS. Okay? Now ADS, we saw, we can think of ADS as a collection of flat spaces so this, upon doing Z goes to L over R, was the original metric that came out of the derivation. So from our brain derivation. Right? Now, I just want to point out something here because many people get confused by this. This space-time as a boundary, and the boundary of this space-time, the boundary of ADS, is here at Z equal to 0, which before corresponded to R equal infinity. Okay? Do you agree? Now, this idea is that there is a theory here. There are strings moving here, strings inside ADS, they move here. This region is called the bulk, and this plane is called the boundary. Okay? And the cartoonish picture, if you want to describe it to some non-physicists, is to say that we have some kind of crystal ball, and we live at the boundary of this space-time, which is this plane, and inside the crystal ball, the strings are moving. And this is this holographic picture. So people say that n equals 4 lives here. Okay? This is what people say. Let me put quotation marks because it's someone speaking. This is where n equals 4 lives. And in the bulk is where ADS 5 times S5 strings live. We can use words. I mean, words, it's okay. They don't do any harm, provided we write correct equations. But we must be a bit careful in the sense that what we don't want to say, which sometimes people go a bit further and they also say it, is that the boundary is where the brains are. Okay? This is just simply wrong in many ways. First, it's wrong because you should not ask this question. When we say that the proton is here, and that we have either a proton or we just have a particle with some non-trivial potential V of R, when you go to this language, you should not ask where is the proton. There's no proton. You traded the proton for a background. Okay? There's no proton. Proton was replaced by the effect of the proton. But if you insist, okay, but I really want to know where was it? If I really want to put it, where is it? Then where would you put it? You put it at R equals 0. Same here. Where are the brains? There are no brains. We are trading the brains by the bulk. But if you really want to put them, at least don't put them at R equal infinity. Put them at R equal to 0. Okay? Some people, they like to put it at R equal infinity. Now, there is some truth in putting it at R equal to 0. At R equal infinity, which is just Z equals 0. Because if you want to say, where is the region where I should put my sources here? Where should I put my sources? If I want to consider some in process and some out process. Well, this is where I should put my sources. I should put a machine here that throws particles here, right? From infinity. And then a machine here that absorbs particles at infinity again. So this is where I put my apparatus. I put it at infinity in the region where it doesn't feel the proton. And I throw stuff in and I get stuff back. So indeed, this is the region, if you want, where the proton starts. By proton start, I mean the interaction of the proton starts to be felt. So if I want to say, what is the entrance of the proton? It's there, it's at infinity. I put some probes there or some projectors. I send stuff in. Now we are in the proton domain, and then stuff comes out. So similarly here, if you want to say, where is the region where the proton starts at infinity. It's where I should throw stuff and get stuff. Okay? So it makes sense that indeed, it's at the boundary of the theory, which is where n equals 4 is. It's at the boundary that we put correlation functions. We put operators here at some position xi at the boundary. That's fine. That's the intuition that we have our boundary. And at the boundary, we insert some probes. And then the probes go inside the background, they interact, and they come out. Okay? So is all this consistent? Hey, if you are not confused, perhaps you became confused and now not confused again. But are you at least not confused as the final state? Yes?
When you're putting the operators there, when z equals 0, are those the asymptotic states of the R?
I'm just saying that when we consider a duality, we have some process in ADS, let me call it Z ADS, right? Some process in ADS. By Z, it's kind of a partition function. We sum over stuff in ADS. And under ADS CFT, there should be a dictionary. So this should be equal to some observable in the CFT, some average in the CFT. For example, I could ask, how do I compute correlation functions? I have two operators. In the CFT, I put two probes in the CFT and I studied. This should correspond in the ADS language to having some strings that go inside, they move, and they come back. So this would correspond to sending a string here that goes inside and comes back. And it's moving from one point to the other, but it starts at the boundary and goes to the boundary at some position x1 and goes to x2. So if I want to draw this correlation function in this picture, I put it at the boundary. Okay? And it makes sense to put it at the boundary, but yeah, I said everything. I don't want to repeat. Is it clear? Now, this space-time, there is another way of thinking about this space-time. Is that saying that ADS can also be thought of as an hyperboloid. This is also ADS. Okay? This is also ADS. What is an hyperboloid? Let's write. So we have some condition. Y minus 1 square plus y0 square minus y1 square minus y2 square minus dot 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 minus y5 square equal to 1. If we want to describe ADS5. Okay? So we think that we are thinking now as ADS5 as being embedded in Minkowski space with 2 times and 4 space directions. So it has 2 times y1 and y0. And it has 4 directions that are space-like. And we put an hyperboloid there. And indeed, if you just compute the metric, ds square, which would be just the flat metric, dy dot dy, restricted to y squares that obey this condition, y square equal 1, you can find the previous metric. You can find that metric. If you use a particular parameterization that solves this constraint, let me tell you which one solves this constraint. For example, if you use y minus 1 plus y, sorry, I did something wrong. Here I have 5, 6, 7, 8. It's 4. Sorry, here it's 4. If I have y minus 1 plus y4, I call this 1 over z. Y y mu, where mu runs from 0 up to 3, I call it x mu over z. And the remaining y that I did not parameterize, the difference between the two, you find such that that condition is satisfied. Okay? Then you find the Poincaré metric. Which is just this metric here. These are what are called Poincaré coordinates. So ADS can also be thought of as an hyperboloid, okay? At least locally. And you can ask whether the full hyperboloid is mapped to the full Poincaré or whether this one is bigger than that. You can ask global questions. If I paint here, if I put a point here, I tell what point it is on that picture. Then another one, another one. I mean, which space is bigger? Is one the analytic continuation of the other? Is one smaller and so on? This you did in the homework, so I'm not going to go there. But now that we have this intermediate solution, there is another parameterization that we could use now to solve this constraint. Okay, this is one way of getting rid of this constraint. Another one is to use y minus 1 plus I y0 equal cosh rho e to the it and yi equal sinh rho times a unit vector. So this parameterizes a unit sphere. So you see that these coordinates are in a circle, y1 plus I, y0. It rotates with this radius and this angle. So if I put a minus here, of course I just put, so let's put here plus minus plus minus. So these coordinates are in a circle of radius cosh rho. And then this yi is in a circle of radius sinh rho. Cosh square minus sinh square is equal to 1. So this solves the constraint. So the way we think here, in this hyperboloid picture, is that what I drew here were these two time-like directions, y0 and y minus 1. And I'm at a fixed circle here. So this direction, in this direction, rho increases. And if I am at a fixed rho, this t rotates here in the hyperbola. And I can ask myself, how does the metric look like in this case? And the metric, when I use these coordinates, ds square becomes minus cosh square of rho dt square plus d rho square plus sinh square of rho, the metric of a 3-sphere. This is what are called global coordinates. Global coordinates, we should now picture them as follows. We draw a cylinder. Okay? And now this direction here is time. Okay? This direction is time. This radial direction is rho. Rho equal to 0 would be being at the center. Right? And this line here, a constant line here, represents a 3-sphere. So I can only draw an NS1, but in higher dimensions, you should think this as a 3-sphere. So you see that as rho goes to infinity, indeed, as rho goes to infinity, this metric becomes minus e to the 2 rho times, or plus, and then minus dt square plus the metric of a 3-sphere. Okay? So the boundary of this space-time is not Minkowski, but the boundary of this space-time is time times the 3-sphere. So this is the boundary of ADS, of global ADS. So in this language, it's kind of an analytic continuation. The space is bigger than the original Poincare patch. But once we have this, we can enlarge it and get to this bigger space-time. And this is what we, in the exercise, we call the gravitational box, in the sense that if you consider geodesics that go through the origin, they come back, and then they oscillate, and they keep moving like this in time, and they stay inside this box. And if you send light rays, they barely touch the boundary, and they come back. This is another way of thinking of ADS. So the boundary of ADS, when we think from the point of view of Poincare coordinates, is Minkowski space. The boundary of ADS, when we think from the point of view of global coordinates, it's R times S3. And there is a simple way of drawing both pictures, which is to draw in these global coordinates, where is the Poincaré patch? If I draw all the points that I can parameterize, so I pick any point there in Poincaré coordinates, and I draw it where this point is in this cylinder. Okay? So any point, I take any x mu, any z, and I plot it here. Okay? Which you can do. You know how to go from Poincaré to y, from y to global, so you find the map global to Poincaré, and you do it. And you did it in the exercise. And what you find is the following. You find that that boundary there at z equal to 0 is mapped to a napkin that you let me see if I can draw, that you put around this cylinder. So you have a napkin. If I can draw it. Trying to draw. You see what you do? You take a square like this, and you just wrap it around like this. Yeah? You just do this. So this surface here is the map of Minkowski space, of this z equals 0 in the previous picture. And then there is some surface that I could try to draw here, but you have some nice picture, some surface here, and some surface here, such that here there is a volume inside, right? And this volume is what the Poincaré metric covers. So this is the region covered by the Poincaré coordinates. So this is why people call it S global. It's bigger. It contains a small, the Poincaré coordinates. They parameterize this particular region. Okay. Do the same thing as in cosmology, right? Sometimes we do some coordinates that describe part of the space, then some coordinates that extend beyond the horizon, and so on. So it's the conventional stuff. I'm not doing anything very esoteric. Okay. And in fact, I just want to make a comment because it's something that is actually well known to mathematicians, what's going on here. We can think that on this here, we add a CFT in Minkowski space, in this plane. Okay? And Mach and Luscher, two mathematicians, they worked out whether there is a natural analytic continuation of a CFT which enlarges this Minkowski space. So you now forget about ADS. You just ask, I have my CFT, which is defined in this causal square. Is there an analytic continuation where I take one point inside my square, another point outside, in the boundary of the cylinder? Okay? And indeed, they found that there exists such analytic continuation. So a CFT can be analytically continued to the full cylinder, where by cylinder I mean boundary of the cylinder. I don't know, a cylinder, is it the boundary or does it include the inside? Ball includes the inside, right? And sphere is just the outside. Cylinder, is it just the outside or is it the inside as well? Anyway, you all understand what I mean. A CFT can be analytically continued to the full cylinder, to this full part. And how do you do it? You do it by putting more napkins, right? You just put a next napkin here on top of this one. That would go here. This would be another Minkowski space. You put another napkin here that goes around here. So this would be Minkowski minus 1. This would be Minkowski plus 1. And this would be Minkowski 0. And then you put another napkin, and you just start wrapping it with napkins around. Okay? So you can include these infinite copies, z to the n times Minkowski space, okay, where you can put them for n positive upstairs and for n negative downstairs. all together, they form this R times S3. And they gave them nice names. They call this upper one. These are called spheres of heaven. And the bottom one are called circles of hell. So this is mathematical terminology. We should adapt it. Okay? And the idea is that a CFT can be analytically continued from the original domain to these spheres of heaven and circles of hell. And when you do it, the full analytic continuation describes R times S3. Okay. So the idea is that actually, by just following this chain of analytic continuations and so on, that you can do either on the CFT or on the bulk, we actually get the following. We get that n equals 4 super Yang-Mills in Minkowski space is dual to AdS5 times S5 strings in Poincare coordinates, which is in Poincare space. Let me call it space instead of coordinates to indicate that it lives in, it's that space there, which when thought of from the cylinder point of view, it's a subsection of the total space. But we could do something else. We could consider our quantum field theory, n equals 4 super Yang-Mills, but not put it in Minkowski, but put it in a nice spice. Consider time, but put it on a compact sphere. Don't put n equals 4 on an infinite plane. Put n equals 4 on time times a sphere. It's a nice thing to do. You put it on a compact manifold. The spectrum will be discrete. Everything is more regularized. No infinities, nothing. It's much nicer. You could do it. I mean, if you are a mathematician, you would definitely prefer much more to put a theory on a finite sphere than on an infinite plane and so on. And this would be dual to AdS5 times S5 strings in global coordinates, in global ADS. And these two theories, like those are not independent, they are analytic continuation of this other, these two can be related by a so-called Weil transformation. Weil transformation is a transformation that rescales a metric at a point G, at a point X, to omega times the metric at that point X. And there are Weil transformations that map you from flat space to a sphere times time. And if you follow the implications of these Weil transformations, they tell you how quantities here go to quantities here. What is a natural quantity on the top? It's the spectrum of anomalous dimensions in Minkowski space. What is a natural quantity when you put the theory on R times S3? You put it on R times S3. Now the theory is like quantum mechanics in a compact space. It has a spectrum, energies, where energies are just the eigenvalues of dt, right? Just the usual. There is some Hamiltonian that gives evolution in time, right? Just a system in a sphere, and there is an Hamiltonian that evolves in time. And this Hamiltonian has some eigenvalues. And under this Weil transformation, the two natural quantities are exactly the same. This goes to energies of n equals 4 super Yang-Mills when you put it on time times the sphere. Okay? If you want to be picky, you would say that deltas are numbers, but energies have dimensions. So what could be the way out? Sorry? Yeah, you would just, there is some L missing, right? Just to make sure things are okay. So it's energies measured in units of 1 over L, of course. Okay? But this L we set to 1 because we know where to put it. Yes? This is just usual radial quantization, but I don't want to use those words because some of you did not have CFT. Is it okay? But now what are these energies? These energies, they are the eigenvalues of dt, right? where this is time. Right? But this same time, this is the same time that is here. Just at the boundary, it is the time of the boundary theory. But it's the same t that you use inside. And this t is a Killing vector, right? See, nothing depends on t. So in the bulk, inside my cylinder, it's also very natural to ask, what about the energy of my strings in the bulk? But of course, the energies of strings, what are they? They are again the eigenvalues of the same operator dt. So it's the same operator dt, so they are the same. So this is the first example of a very sharp dictionary that I'm giving you here. Right? Because we had these theories are equal, but we said we need a precise dictionary. And here is a dictionary. If you want to study the spectrum of all dimensions in your CFT, compute all possible string motions and compute all possible string energies as measured with respect to ADS global time. Is this clear? So this very important quantity in the CFT, now forget about the intermediate step, is equal to take all possible string solutions, compute another charge associated to translation in ADS global time, and this, they are in one-to-one correspondence. So that goes back to this question. Here, we knew what we had to do. Here, it was all about diagonalizing some Hamiltonian and computing some deltas and so on. But when I was drawing these pictures, you should have complained, okay, I have this picture, but what exactly am I computing on the string side? Well, in the end, that's what we aim at. What we want is to study, given some state of the string, what is its energy? But then it's exactly the same question as in the spin chain, right? Given some state on the spin chain, what is its energy? So now, at finite coupling, given a state in this object that we call it not spin chain, not string, but spring or whatever, we call it some funny name, the question is, what is the energy of this object? So this would be the grand question. What is the energy of this object at finite coupling? Yes?
Using the flat connection for the fast strings, what would the energy be? How is this translating back?
Yeah, very good. So it's a good question. So remember that how did it go in the spin chain case when we considered classical solutions? When we considered classical solutions, we saw that classical solutions of the spin chain were mapped to algebraic curves, were mapped to finding all possible p of u, all these functions p prime of u. And we said, make a list of all possible algebraic curves, and then go to that algebraic curve, and there is a point around which you expand and you read off the energy. Here to be the same thing. Find all possible eigenvalues of the flat connection, of the monodromy of the flat connection. Not by computing it solution by solution, but rather by making a list of all possible analytic properties and just making a list. And then you have to ask, around which point do I get these local charges, which is related to the question in the beginning. And you will find that there is again a point around which you expand and read off the energy of the solutions. So at least at the classical level, things are very similar. You have algebraic curves here and algebraic curves here. There is a point around which you extract the energy. There is a point around which you extract the energy. Now, they don't need to be exactly the same, because this is one regime of the theory, this is another regime. But it's very good that it's very similar. It's very good that it's very similar. And this allows us to follow states, because we take one algebraic curve, and there are some things that should not change as we go from here to here. So the way to think about this is that these curves here, let me just make a parenthesis, these curves here came, you remember, from some condensation of many solutions of Beat equations that were given this cut, and then by integrating P, we could measure how many excitations there were on this cut. Now, the idea is that now we increase the coupling, these solutions will move of the quantum Beat equations, and will condense into a slightly different cut at infinity. But how many excitations are there inside the cut? The same. This doesn't change. So this n, this kind of n, will be a good quantum number at any lambda, and it will allow us to take a solution at weak and strong coupling and match both and say these two are the same thing. It will allow to identify which one is which. So they are the good variables, for example, in this classical. Okay. Very good. So now I want to show you how sometimes, indeed, using integrability, we can go very far into solving a theory, even if the theory is not weakly coupled. Okay? So right now we found classical strings. That's classical theory. We know very well how to deal with classical theory. We saw one loop spin chains, which is a weakly coupled, one loop Feynman diagram, and so on. But now the bar is high. We want to go and understand the theory at finite coupling. Okay? So let's consider an example of a strongly coupled theory and its solution using integrability. Okay? That's what we are going to do now. And we are going to consider a toy model that is inspired by the model that we really want to solve in the end. So what would be our dream? Our dream is to compute the string path integral, which will be an integral over some fermions, over some variables u in the sphere, where u square is equal to 1, over some fields v in ADS, where some v square equal to 1, this with an ADS signature, and this with a sphere. And then exponential of minus some square root lambda, some string tension, which is related to square root of lambda, times, let me write what you would do, time, for example, some term that would put just some fields on the sphere, lambda being a Lagrange multiplier. Let me use some different letter. There is lambda there. Let me use capital lambda. Capital lambda being a Lagrange multiplier that when I integrate over it, again, it's implicit, we set u squared to 1. And then there would be plus the ADS part plus the fermions. Okay? And what you actually saw in yesterday's lecture was that if you take just strings, this kind of toy model, which we can think just, which is what is called this part, is the O n, where n in this case is equal to 6 sigma model. We saw that even just taking this part, we could find some flat connection. And you saw that it doesn't matter which ON it is or whether it's an hyperboloid, and so on. So what I want to tell you is let's take a toy model and do something a bit drastic, which is let's just drop this part. Now, classically, this is fine. I can consider solutions just moving in the sphere. Of course, quantum mechanical, it's nonsense. But it just gives me a simpler model that I can try to study. Okay? The other one is more complicated. The other one we'll do tomorrow, more or less. But this one already should look very hard. Okay? So this is our toy model. So we forget about this, and we are left just with the rest. So we want to study what is called the 06 sigma model at the quantum level, and as you see, it's well motivated. It's not that far away from what we want to do. Okay, so today and tomorrow we will solve this 06 sigma model. I wanted to do it today, actually. This was my starting of my lecture. But I forgot there were some small epsilons, but I'll be fine. Okay, so we want to solve this theory. Now remember that even the equations of motion are hinting that this is a hard task. What are the equations of motion? So the equations of motion tell you that box of u, Laplacian of u. If there was no Lagrange multiplier, it would be just box u equals 0. But because of this Lagrange multiplier, we get that box u is equal to Lagrange multiplier times u. And then you have to solve for the Lagrange multiplier. For example, you dot the equation with u and you massage a bit, and you find that this is what the Lagrange multiplier is. And this is the equations of motion. Now, what we want to see from these equations of motion is that the theory is nonlinear. It's very nonlinear. It's not something we can solve. These kind of equations are very complicated. It's not something where there is a weakly coupled parameter, some lambda, some g, that I can put g to 0 and then I get some Laplacian, and then I start doing perturbation theory. There's no such thing. There's no parameter. This is a strongly coupled theory. You cannot just take this u and start decomposing u into modes, doing Fock space analysis, doing weakly coupled perturbation theory. You just stare at this equation and you hide. What do you do now? Now you panic. Oh my God. Strongly coupled? I don't know. You just don't know. You open a book, there is nothing there. So how do we deal with a strongly coupled field theory? In fact, this is a very good question, and in general, there's no good solution to this question. We can even ask, what are particles? What is a particle here? What is an excitation? What are particles? Okay? So we can ask, what is a particle? What do I mean by this? Of course, a particle is this. Right? This is what a particle is. But more precisely, it's moving, and it has some energy as function of momentum. What is this energy as function of momentum of a particle? And if the theory is free, we just write some free scalar field with some mass m. This is just square root of m squared plus p squared. But what about here? The theory is not free. What is this dispersion relation? What is this particle? But more than that, does it have some kind of degree of freedom? Is there some index A that transforms in some representation of SO6? Right? It's very natural to expect, for example, again, if this was just a mass term, particles would just be vectors that transform under the vector representation of SO6. But here it could be more complicated. Strongly coupled dynamics could tell you that particles transform in the symmetric representation of O6. So these typically are very hard questions. And I can give you quantum field theories for which people had to guess and then check and so on, and for which they don't have very good evidence for this question. Here, we are in better shape. As I will tell you, there is a tool that we can use to get an idea of, to kind of see more or less what the answer to this is. But I just want to point out that even these very, very basic questions, what are the relevant degrees of freedom? What is a particle? How does it transform? In which representation it is? These are very tough questions that the Lagrangian can often tell you almost nothing about. Where it's the strongly coupled dynamics that will tell you what is going on. And roughly the Lagrangian, for some things, is more or less useless. But that's life. But here, the Lagrangian is useful, but we have to be inventive and think of a trick. And the trick is to think that 6 is very large. Right? 6 is a very big number. So let's treat this n, let's think of n as being much bigger than 1. And let's do an analysis at large n. That, I mean, if it works, if these kind of things work for QCD, where n is 3, I mean, n is 6, it's really precision spectroscopy, right? So we are doing n equals 6, and we'll try to see what is this large n telling us about how we should think about this theory. So let's go. Let's be more explicit and remind ourselves that we integrate over the Lagrange multiplier, of course, to set the constraint. We typically don't even write it, but let me write it down. And now, let me do something funny. Instead of integrating over the Lagrange multiplier, let's integrate first over the field u and keep the Lagrange multiplier to the end. Then we go on, we write an equal sign, and we get integral. We integrate over the Lagrange multiplier that depends on sigma and tau at the end. But first we integrate over u. And what do you get after integrating over u? I want to put whatever we get in the exponent. So what do we get in the exponent? We get, so there is one term that doesn't have u, which comes with that -1. You see the -1 inside this constraint. This -1 multiplies the minus outside and gives square root lambda over 2 pi integral of the Lagrange multiplier. That's easy. And then we have the integration over u. What does the integration over u give? Good. So as you are saying, we are doing a quadratic integral, so we get a determinant. So we'll get a determinant of box plus lambda, right? But it's in the exponent. So how do we put things in the exponent if they are not in the exponent? We put a log. Very good. And this is still wrong. Because do we get determinants? Sorry? I think let's see, it. So if you do x equals square root, yeah, there is minus. But what else? It's 1 over determinant. Is it 1 over determinant that the Gaussian integral gives? Sorry? A half. That's good. It's square root of determinant. But what else? There's something important missing here. Sorry? No. No. Sorry? We are doing this Gaussian integral, right? Of how many fields? Small n, right? So we do for u1, u2, u3, so small n. And this small n is critical. Because now, if this guy is large, we can use saddle point. Now we have a very big action. So it means that we can use saddle point. We do variation with respect to lambda. And the saddle point equation we get is variation of the first term just gives square root lambda over 2 pi. And this is equal to n over 2 times variation of log det, which is, of course, trace log. Right? These known identities for log det are trace log. And if you take a derivative, you just get the trace is just integral d2p. This is the trace, if we go to momentum space. And we take derivative of a log. So what we get is downstairs p squared plus lambda. Okay? And, I hate this notation. Let's see, we do this integral up to some cutoff that I will call 1 over a. This is the cutoff. Then you can easily see this integral can be estimated to be n over 2 log of Lagrange multiplier. So cutoff is some length. This Lagrange multiplier is an m square. M square now likes to be multiplied by length times a. Yeah. And therefore, this Lagrange multiplier is equal to e to the minus, well, if I keep track of all the signs, there should be a minus here. I don't remember if the minus is here or here. The final expression will be correct. E to the minus 1 second. I cannot read what I wrote, but okay. But I know what it should be. So it should be 1 over a e to the minus square root multiply by that, divide by that, put a minus, exponentiate. Yeah. E to the minus square root lambda over pi small n. Yeah, something like that. This is what is called dynamical mass transmutation. It's a phenomenon by which we started with a coupling lambda, dimensionless, and we went from here to a mass, something with units of mass, 1 over a, lambda, this Lagrange multiplier, which is expressed in terms of the cutoff. Okay? So, I want to point out a couple of things. First, this is non-perturbative. You see what we get here? We get e to the minus square root lambda, which is 1 over the coupling. So this is like e to the minus 1 over h bar. So this is a non-perturbative. It's what's called non-perturbative dynamical mass transmutation. And now what is the physical picture therefore? The physical picture is that lambda now will go to this expectation value of lambda that we just computed plus fluctuations, plus small fluctuations. Okay? And we saw that there was a VEV that we just estimated, which is non-perturbatively generated. Okay? Let's call this VEV, let's define it, let's call it m squared. Yeah, this should be an m squared. There should be an a squared here, actually. And here an a squared. So that the units are right. Let's call this VEV m squared. Okay? Then, what we are concluding is the following, is that this thing here will acquire a VEV, a vacuum expectation value, equal to m squared, plus small fluctuations. So now we can read off very well the physics of what's going on. What's going on is that we will have n particles with some mass m, which is dynamically generated, plus some small interactions. So the large n analysis tells us that at large n, we get the answer to this question of what is a particle is very simple. We get a particle which has dispersion relation epsilon equal to m cos theta and momenta equal to m sin theta, where theta is just a useful variable to parameterize a relativistic particle. This m is not trivially related to the parameters of the Lagrangian. It's something dynamically generated. It's this non-perturbative effect. But we just call it m, and it becomes our parameter, our physical parameter. We don't care very much how it relates to the bare parameters of the theory, because it's physical. And this particle moves with some moment, and furthermore, indeed, it has some index a, and this index a transforms in the vector representation of SON. So now we know what a particle is. A particle has an index a that goes from 1 to small n. It's a vector. It's a relativistic particle, and the mass is an unperturbative effect. So if the coupling is very big, for example, it's a very small mass. This square root lambda is very big. Is it okay? Now, out of all this discussion, I'm actually not going to need most of these details of this saddle point and so on. This is why I was fiddling a bit and not remember exactly where the factors are, because these are all irrelevant. All we need to take out of this discussion is that now we know what a particle is. We know a particle. They transform in a vector representation of SON. Indeed, we know. And we believe, we now conjecture that for SO6, this qualitative description is correct. That there will be 6 kinds of particles transforming in the vector representation of SO6. They will be relativistic with some mass m non-perturbatively generated, and we will measure things in units of this small m, mass m, and we don't care what's the relation between this mass and some parameter that we write in some human-made Lagrangian. Okay? Very good. So now, now we can use the power of integrability and of symmetries. What do we want to do? So we solved the first problem. Now we have epsilon of theta is equal to m cos theta, and p of theta equal to m sin theta. This is just statement that this is equivalent, of course, to saying that epsilon is square root of m squared plus p squared. So we know the dispersion relation. Now, why is this variable theta useful instead of using p? Because boosts are translations in theta. That's why people introduce this rapidity. So this is kind of useful because, for example, if I want to study what is the S matrix of two of these particles, it should be boost invariant. It should be Lorentz invariant. So it can only depend on theta 1 minus theta 2. So this is great. So let's try to find the S matrix between two particles with indices I and j and outgoing indices k and l. Okay? And what do we know about this theory? Well, we know it's Lorentz invariant. So it only depends on theta 1 minus theta 2. That's great. It's a function of one variable. That's very good. We can say that it's equal to some function, sigma, of theta, theta being the difference of the two rapidities. And then, just based on SO6 symmetry, I can write something times the tensor delta ik, delta jl. This is one tensor I can write. I can write delta il, delta jk, or I can write delta ij, delta kl. This is all I can write based on SO6 symmetry. And then I have coefficients behind each of these tensors. But if the theory is integrable, which we know it is because we computed all these charges and we know it's integrable, we know that all these three coefficients, we already computed them in the lecture because we already studied the R matrix for the SO6 spin chain. And even though we emphasize that the physics has nothing to do, an R matrix and an S matrix, they are different physical objects, picture-wise, they are the same. So we already computed the R matrix. We already saw the implications of imposing for the matrix part this equation. And we saw that this fixes the coefficients of these tensors. So we can write them up to an overall constant, which I will choose some normalization, which is convenient, as you will see. And what we get here is then that this gets 1 over 1 plus x. Let me tell what x is in a minute. Here we get x. Actually, I have to check if they are exchanged. Let me see. So this ik b would be. So let's draw the picture. Now we have to be specific. What do we mean by this? Now it's our choice. We want to understand what process corresponds to this process, which we think that the particle theta just goes through and the color continues. So do you want to call this identity or permutation? Now it depends on our taste. If we think that we are sitting on top of the particle, this of course does nothing. Particle just goes through, particle just goes through. So this would be I, if I put here I, j, k, l, this would be I go to L, not I go to K. So I go to L, j goes to K is what we call identity, and then it's okay, it's B. Good. And if we use that convention there. And then for the next term, we have 2x over 2x plus n minus 2 times 1 plus x, where x is just basically theta up to some overall parameter that is not convenient to write all the time. That's why we take it out. I over pi times n minus 2 over 2 times theta. And for us, n is equal to 6. But we can do it in general n even. So this here, what fixed this normalization? This normalization is fixed such that if I call this R matrix of theta, I'm using the normalization that R of theta times R of minus theta equal to 1, which in pictures would mean unitarity, that if I scatter twice, it's the same as doing nothing. Okay? This is just fixing this nice physical normalization. So that's why I divide everything by 1 plus x compared to what we saw in the lectures. Okay? Of course, I can absorb whatever I do in sigma, but this is a nice normalization. Okay? So you see how powerful this was. Studying this theory was reduced to finding one single function. Everything else is fixed by Lorentz invariance, unitarity, Young-Baxter. As soon as you say the theory is integrable, who cares about the Lagrangian, you see? It's way more powerful. Were we to start using the Lagrangian, we would suffer a lot. But here we just said, well, it's integrable, so I know what the result must be. The relative coefficients must be this and that, and so on. And I have to find this function sigma. Okay. So let's do it in a way that that will generalize easily to the system that we want to study tomorrow, which is the ADS-CFT system. Okay, so these A, B, C are all fixed by Young-Baxter. And the basic idea is the following. Now we want to use what is called as crossing symmetry. Okay? Now we want to use crossing symmetry, which is now there is a nice way of thinking about crossing symmetry that is not the conventional way, but it's very useful if you can do it, which is the following. Suppose you can create a spurious state. So let's create a spurious singlet. So this is a spurious state. It should be nothing. And what is this nothing? This nothing is just a singlet state, I sum over j equal 1 up to 6, of some state with index j, some state with index j. So I sum over all j, so it's a singlet. And here I put a particle with rapidity theta, and here a particle with rapidity theta plus I pi. So what is this state? This is a two-particle state that has no color at all. If I try to measure its color, I find nothing. But it's a pair of particle-antiparticle. So it also has really no energy and no momenta. It has no nothing. It's nothing. So indeed, if you compute the total energy, you get m cos theta plus the energy of the antiparticle, which is m cos of theta plus I pi, which is equal to 0, and the same for the momentum if you replace just cos by sinh. So this is a spurious state. It's really this. It's like we are moving here, and all the time we are producing pairs of particle-antiparticle, and we better not need to take these particle-antiparticle pairs into account. So what we want to impose is the following. We draw this state like this, saying that out of the vacuum I produce this spurious state, where I sum over the possible colors I create to make a singlet. And now I say that if I take my particles and scatter them through, this should be immaterial. It should be the same as just not scattering at all. Okay? This is a nice concept because you can see that it generalizes if you don't have, strictly speaking, Lorentz invariance. what's crucial is the possibility of constructing a spurious singlet state. And you might have some theories where the dispersion relation is a bit more general. It's not exactly just as simple as this. But for which you can also see that, oh, there is a point where energy goes to minus energy, momenta goes to minus momenta. This is what you would call antiparticle. And it is not so crucial if you have Lorentz symmetry or not, whether you can really rotate and get the same theory. What matters is the possibility of constructing this spurious singlet state. Okay, good. So now let's suppose that we then measure the outgoing state. So we put some detectors here, a detector here, a detector here, and a detector here, and the same thing here. And we will measure the external state. So let's say that we measure here an orange particle. And here, if we want to say it's the same, here we should measure also an orange particle. I'm choosing orange to indicate it's one of the indices. And here I measure some white particle, which is another index. And here I have to measure the same white particle. So more or less what's drawn in the picture. Okay? So now let's write what could happen for this to happen. What could happen is the following. One process is what is drawn here. Okay? One is what is drawn here. Let me draw it again. And let me draw this line like this to indicate that what does it mean here? It means that here we are using this B of theta, this element B of theta, where particles just go through. And what about, you see, this is the arrows coming in. These are the arrows. And what about here? Here we are using B again. Let's be more careful with the arguments. Let's say here I produce a particle, and it's convenient to do the following. Let me put minus theta, and here minus theta plus I pi. And for this orange particle, let's say that it has rapidity theta equal to 0. It's at rest. Because what matters is boost invariance. I can always boost everyone. So now you see 0 minus theta gives theta. So it's B of theta at this intersection. And here it's 0 minus theta plus I pi, so it gives B of theta minus I pi. Okay? This is what this diagram gives. Times sigma, because sigma is outside. So all this that we are going to draw, there will always be sigma, so all this is multiplied by sigma of theta times sigma of theta minus I pi. Okay? Okay, so B we know, so we just multiply these two. But there is another possibility. And the other possibility is that the red line, let me draw very light. And now let's fill. The other possibility is that the orange line does like this. And the white line does like this. Okay? What are we using now? Now, these two particles here, they annihilate. So we are using here, which one is the annihilation one? Yeah, which is which one? C of theta, good. And what about here? Here they deflect, right? So which one is here? Yeah, this would be what we call that I goes to J, so this is A of theta minus I pi. Right? So I just wanted to do it very, very explicitly, such that you could see that now the equation we have to impose is just literally this expression equal to 1. Because 1 is what we get if we take this picture here. Nothing happens. And this part here inside this bracket is literally just this function times this function plus this function times this function. You have them there, you compute, and you get the following. You get that sigma of theta, I will shift this equation by I pi over 2 to become nicer, plus I pi over 2 times sigma of theta minus I pi over 2 is equal to theta plus probably not correct. One sign is wrong. So this is what the inverse, this square bracket gives the inverse of this. Okay. So this is something powerful, you see? And we also know by unitarity that because we normalize it in that way, that for sigma we should also have that sigma of theta times sigma of minus theta is equal to 1. So you see, without using any Lagrange and anything, we are very far away. We are already very far. All we have to do is find a function that solves this functional equation. Okay? So now, given time, I will do this properly tomorrow, but I don't want to cut the logic. So now, we start with this box. No. So we have this box with our equations. Then it follows some work that we are going to do tomorrow, because I do want to teach you how to deal with this kind of equations. These are equations that will appear in many situations in physics. Okay? So you suffer a little bit. You solve this. It's not hard. It takes 1.5 pages. So we will do it in 10 minutes tomorrow. And we will get that sigma of theta so we do some work, and we get that sigma of theta is equal to this. Sorry? Tangent. I don't know. What do you use? It's the same. And these are gamma functions. Okay? These are gamma functions. Everyone knows what a gamma function is, right? Very good. So you see, it's not a trivial function. It's not a parabola or a cosine. It's a complicated function. It's an untrivial function. And this is the solution indeed. The claim is that this is the full non-perturbative solution of what is the full S matrix of the 06 sigma model. See, we just solved this strongly interacting theory in half an hour. See, this is the S matrix that describes scattering of these excitations. Okay? And just as a final application, such that we write some formula of what we would now use this for, let me give you an example. Let's now suppose, as an application, that we take a bunch of particles. Let's consider an experiment. Let's take a circle, and let's throw a bunch of particles in this big circle. Okay? So this is a circle of some big circumference L. By the way, what would it mean to say that L is big? L has dimensions. So how should if I want to say L is big, what should I write? Sorry? I think I heard the correct result. I'm not sure. So what should I write if L is big? I say that L is much bigger than what? What sets the mass scale? The mass of the particles. So I said that the L is much bigger measured in units of the mass of my particle. Suppose I do this, and furthermore, I consider particles for which the index that are all not pointing in the same direction. That's not what this picture means. This picture means that for this index of my particle I choose a linear combination of 1 plus I2. This is the analog of, you remember that we construct this complex scalar Z from phi1 plus I phi2. This is like giving a charge. It's not putting it pointing in one direction, but rather giving it some spin. Giving it some charge. Now, why this is useful? Because now we can really think of each of these particles like a subsector of my theory, where each of them is like an SU2 spin pointing up. Okay? Now, what happens when I act with my S matrix on two spins pointing up? And I get something here as the outside state. And the point is that this outside state must be up, up, and therefore this is a closed sector. Because this is the same as before. If we start with something that is symmetric and traceless, and remember, why is this traceless? Because precisely of this I here. So you remember, we multiply two fields and say 1 with 1 gives minus what 2 and 2 give. So if I act with a trace on this object, on a pair, I give 0. If I act on permutation, I get the same thing because both are up. And if I act with identity, I get the same thing because identity is the object that does nothing. So here, this is a closed sector. I act with up, up, I get up, up. So in this subsector, it's very easy to ask what happens when I scatter a particle through everyone else. Scattering a particle through everyone else, because everyone is just up, I can ignore the degree of freedom. I just see that they are normalized such that 1 over 1 plus x over 1 plus x is 1. Right? The sum of the first two tensors, which is identity and permutation, is normalized such that it's 1. And therefore, I conclude that if I do this experiment of putting particles in a big circle, here is what I get. The energy is given by sum of how many particles I put of the mass, which is dynamically generated, times cosh of theta j, where for this theta j, I can write the equations right away. E to the I mass times L, which is my dimensionless parameter, times sinh of theta j, times product over k not equal to j up to n of my sigma of theta j minus theta k equal to 1. So now, you see, all we have to do is solve these bit equations, and if the circle is big, we get the spectrum of the O6 sigma model. This will be very much the kind of things we'll be aiming at. So this is the kind of things we want to repeat for the full ADS-CFT system. Is do some kind of arguments like this that will land us directly on the finite coupling full result for what should the energy be. Okay? And there, for example, in that particular example, this box is what I told you when we studied the Heisenberg spin chain, that these are really the key ingredients in studying the model, is knowing the dispersion, then we can write what the energy is, and knowing this matrix, because then we can write down bit equations. Of course, here we see right away that what are these particles? They are some non-perturbative object. We should not think that they are a point like our magnon. They are more like some Gaussian, like some bump. Right? It's a more complicated thing. And that's why this circle needs to be big. Because if this circle is very small, these tails of these particles, the fact that particles have some finite extension, starts to be felt. And therefore, this box is wrong. So there will be corrections to this box that we can write, plus order, but these corrections will be exponentially suppressed, where this effect I can think of as thinking that I have my cylinder, and I can have some virtual particle going around the world. And these virtual particles going around the world, it costs the mass of the particle, that is, in my theory, times the length. Right? If I can have these virtual effects of the particle going around the world. As soon as I can start having these effects, the particle knows that the volume is not very big, because it knows that it starts moving and receiving effects from this wrapping from going around the world. So there are two challenges. One, find the analog of this box for ADS-CFT, and the other one, ask ourselves whether we will need to work a bit harder in case we want to study volumes that are not very big. Okay? This is the basic sketch on how, without too much work, just the power of symmetries and integrability, we can solve strongly coupled quantum field theories that otherwise we would really not even know how to start. So this gives you an idea and how important it is to have symmetry, Young-Baxter, this kind of crossing, and so on. Yes?
In the two boxes you've got over there, if I set theta equals 0 on the right one, I don't get 1, I get -1. And it's like theta of I pi on 2 times theta of minus I.
Yeah, good point. There is a minus that I forgot here.
Oh.
Yeah, you saw what Tom was saying? If I put theta equal to 0 on both equations, I was getting an inconsistency. Actually, I was not.
Well, if you set theta on the left equation, you want theta equals I pi on 2. On the right equation, you want theta equals 0.
No, yeah, that's right. Anyway, the minus is there. I forgot the minus. If you take, again, the right-hand side is not something mysterious. You just do, you can do it in mathematics. You take b times b plus c times a, where b and c are this. You just take this, and it's what it is. You can check that I had forgotten a minus sign, and that right now it's correct. And actually, let me just tell you, this was choosing some external states to measure our process. We could have chosen something else. We could have measured, for example, orange, 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 and impose the same thing, that the process, that this picture, where all lines are orange, give the same thing. The equation I would get would naively look a bit different, because now different interactions could contribute and so on, but I better get the same equations. So if you remember in the beginning of yesterday's lecture, I was asking people to check some equation in the blackboard. I was exactly checking whether this was working out or not. And of course it is. More questions?
Why is there annihilation terms? I thought it's SO6.
Why there is what, sorry?
Annihilation terms.
The third term, yeah, there is. Why not?
Yeah, I thought the charge is conserved.
These particles are real particles. They can very well annihilate. They are their own antiparticles, if you want. They don't have arrows. These lines don't have arrows. I mean, we can put an arrow to indicate that they are incoming and outgoing, but they don't have arrows in the SU2 sense of conservation of charge. They get an arrow when I consider complex combinations like that. If I take complex combinations like 1 plus I2, now this has a symmetry of a U1 symmetry of rotating U1 into U2. This U1 symmetry defines a charge, and this charge is conserved. So I cannot start with something which has U1, which was 1 unit of U1 charge, which is 1 plus I2, and produce something with 1 minus I2, which would spin in the opposite direction. This would have the wrong charge. But before I construct such complex combinations, which is charging under this SU1s into these U1s, particles are real, and I can perfectly well draw these diagrams where they annihilate, which is just a statement that if you have delta functions of SON, all these three tensors are allowed. Right? Properly applying symmetry just means that you don't draw tensors with wrong indices, and it just means that you are drawing proper tensors.
How can you impose the UN?
No, here I just said, let's consider a smaller experiment. It's not the most, I'm putting a circle. Now you could ask, what if you throw particles which point in generic directions? What equations do you get? That's more complicated. But I had a minus 10 minutes. So I chose to consider a subsector of putting a circle. And on the circle, let's put all particles pointing in the same direction. It's a subset of things I can do with a big circle. So tomorrow I will tell you what happens if you put more general configurations in a big circle. Right? Because here there was a simplification that even though we were dealing with a matrix, in practice the matrix structure was irrelevant at the end. Because you scatter 2 up, you get 2 up. It's just a number. But what about the most general case where you take a particle, you scatter it, and whenever it is scattering, there's really a matrix process being involved. So then what replaces those very simple scalar equations that we put in a box when we have this complicated matrix structure going around? That we never faced yet. We need not answer this question yet. So far, particles did not have internal degrees of freedom. They were just magnons, and it was much simpler. Okay, so I hope this was very sharp because we had a few lectures of hand-waving arguments. Okay, today we have gamma functions and tangents, so it's the extreme opposite. Okay, see you tomorrow.